This question is about the reactions of hydrogen peroxide H2O2. Part A. Hydrogen peroxide H2O2 iodide ions I- and acid H+ react as shown in the equation below. A student carries out several experiments at the same temperature using the initial rates method to determine the rate constant K for this reaction. The results are shown below. Part I. Determine the rate equation and calculate the rate constant K using units. To start, let's write a general rate equation for this reaction. A general rate equation for this reaction will be rate equals K and then each of our reagents, so H2O2, I- and H+. We then need to establish which order each of these reactants are. To do this, we look for where one reactant has increased by a certain value and the others have stayed the same. So, looking at experiments 1 and 2, I- has increased by a value of 2 and H2O2 and H+ have stayed the same. Then you look at rate. Rates increase by a value of +2 or times 2 as well. Therefore, the order of reaction for I- ions is first order. So I would have a little 1 going above its bracket. Then we continue to look. If we know that I- is first order, then when it's dividing by 2, hydrogen peroxide is increasing by times 2 and H+ is staying the same. Well, the rate is increasing by times 1. It's not really changing, or it isn't changing. And if we know that I- is first order, we would expect rate to half. But it hasn't, it stayed the same. And because hydrogen peroxide or H2O2 has increased by times 2, therefore the order of reaction for H2O2 is also first order, so it would have a 1. If we continue, when H+ has increased by times 2 and I- and H2O2 have stayed exactly the same, the rate has not changed, and so the order of reaction for H+ is 0 order, so we'd have a little 0. Therefore, if we write the actual rate equation, we have rate equals K H2O2 I-, and we ignore the H+ because H+ to the power of 0 is 1. Now we need to work out rate. We can do this by subbing in values. So if we take experiment 1, we have a rate as 2 times 10 to the negative 6 divided by the concentrations or initial concentrations of H2O2, which is 0.01 times 0.01. That gives us a value of 0.02 for our K. And then for units, well, we have moles per decimeter cubed per second over moles per decimeter cubed times moles per decimeter cubed. Then we need to cancel these out. So we can cancel out a mole per decimeter cubed, and we're left with 1 over mole per decimeter cubed s to the -1. Another way of writing that is mole to the -1 decimeters cubed per second. For this question, you get a mark for the correct rate equation, a mark for the correct K value, and a mark for the correct units. Part 2. The rate constant K for this reaction is determined at different temperatures T. Explain how the student could determine the activation energy for the reaction graphically using values of K and T. In our data sheets, we get given an equation that links all of these pieces of information together. And that equation is ln K equals EA over minus RT plus ln A. So our first thing when answering this question that we need to do is tell the student to plot ln k against 1 over t. And that means that our gradient will be EA over minus R. So find gradient, and then we could also write in brackets what the gradient is, EA over minus R. And finally, to get EA, we need to times gradient by minus R, which is a value you get given in the datasheet, so you don't need to specify, but then you can write that it equals EA. For this question, you get a mark for each of the bullet points that I've drawn up here. So one for saying plot ln k against 1 over t, one for finding the gradient, and one for saying that the gradient multiplied by minus R equals EA. B. Solutions of hydrogen peroxide decompose slowly into water and oxygen. This reaction is catalyzed by manganese dioxide. Standard electrode potentials are shown below. Using the electrode potentials, explain how manganese dioxide is able to act as a catalyst for the decomposition of hydrogen peroxide. Your answer should include relevant equations. A way to lay this question out is by numbering the equations that we're given. If we use Roman numerals, we can refer to them later on when answering. So first we need to write the equation for reaction 1 and 2. So we can see how using Roman numerals is a good idea, because then you don't have to write them all out. So if we look at their electrode potentials, the more negative, which is 1, that equilibrium would go backwards and 2 would go forwards. So if we combine these, we would have H2O2 plus MnO2 plus 4H plus goes to Mn2 plus 2H2O plus O2 plus 2H plus. We're not finished yet. Because there's an H plus on both sides, these two would disappear and this 4 would turn into a 2. This is our first equation. And then if we write an equation for 2 and 3, again, looking at their directions, well, the more negative this time is reaction 2, and the more positive is reaction 3. So, writing the equation, we would have H2O2 plus 2H plus Mn2 plus 2H2O goes to MnO2 plus 4H plus 2H2O. I'm not writing the electrons here because we know that we're going to cancel them out, and if they were, like say, 2 and 4, then you would need to multiply and scale up the equations, but that's not necessary here, so we don't need to write them. And we would end up cancelling them out anyway, making them even more irrelevant. So the H plus again, the 2 disappears and the 4 becomes a 2. But also we've got 2 waters on both sides, so they would disappear as well. So our reaction equation is pretty small for this one. Now, a bit of reasoning, we would write that the electropotential for I is more negative than 2, so shifts left. And that's enough reasoning. And then to answer the rest of the question, how MnO2 acts as a catalyst, well, we can say that MnO2 is regenerated. And that is enough to get our 4 marks for this question. You get a mark for each of your equations, a mark for referring to electrode potentials and how they shift, and then a mark for saying that MnO2 is regenerated which means that it's able to act as a catalyst. C. Peroxycarboxylic acids are organic compounds with the COOOH functional group. Peroxyethanoic acid, CH3COOOH, is used as disinfectant. Part I. Suggest the structure of peroxyethanoic acid. The COOOH functional group must be clearly displayed. So, the compound that we're drawing will roughly represent a carboxylic acid. And a carboxylic acid, when we draw it out, well, displayed it looks like this. So when we're drawing a peroxycarboxylic acid or peroxyethanoic acid, we can have the CH3 group. We don't need to draw that all out because they're only asking for the functional group. And that would look like this, with roughly a carboxylic acid group being represented, but instead, because it's peroxycarboxylic acid, instead of having the carbon here bond to an OH, we've got it bonding to an oxygen and then the oxygen bonding to the OH, which makes it slightly different to just a carboxylic acid. So for this question, you need to draw the structure completely correct, having the carbon-carbon bonding together rather than carbon-hydrogen here, as I've drawn C3H rather than CH3 and having the hydrogen bonding to the carbon, because that wouldn't work. So making sure we've got this whole correct will get you the mark. Part 2. Peroxyethanoic acid can be prepared by reacting hydrogen peroxide with ethanoic acid. This is heterogeneous equilibrium. A 250 centimeter cubed equilibrium mixture contains concentrations of 0.5 mole per decimeter cubed of hydrogen peroxide and 0.5 moles per decimeter cubed of ethanoic acid. Calculate the amount in moles of peroxyethanoic acid in the equilibrium mixture. So firstly, we need to understand what this question's meaning. A key word in this question is heterogeneous. Heterogeneous means that it's in different states. We can see this in the reaction or the equilibrium that we've been given, because water's a liquid here, peroxyethanoic acid's aqueous, so is ethanoic acid and hydrogen peroxide. When writing an expression for Kc, because we're given Kc here, we use the same states. So our expression for Kc would be that peroxyethanoic acid, because we work backwards when writing an expression for Kc, over hydrogen peroxide multiplied by ethanoic acid. If we plug in values for this, the square brackets in Kc, they mean concentration, and we've got values for concentration. So rewriting Kc, we have peroxyethanoic acid over 0.5 and 0.5 again, because they're the values we've been given as the concentration of hydrogen peroxide and ethanoic acid. We also know that this equals 0.37. So if we rearrange this to get the concentration of peroxyethanoic acid, we would write 0.37 multiplied by 0.5 squared, and that gives us 0.0925 moles per decimeter cubed. If we're working out moles on its own, we would use our equation triangle, NVC. A way of remembering this is Nigel's very clever. And if we were to apply this, we would take the concentration 0.0925 and multiply by our volume, which is 250 centimeters cubed. We want it in decimeters cubed, so we times by 10 to the negative 3 or divide by 1,000. That gives us a value of 0.023125 moles. In our answer, we would write this to an appropriate number of significant figures, 0.023, for example. For this question, you get a mark for writing your expression for Kc, a mark for working out the concentration of peroxyethanoic acid, and then a mark for working out your moles correctly.